cab forward engine. In fact, if you've ever been to the train museum, the only one that was preserved is in the train museum of Southern Pacific's cab forwards. In other words, you know, most of these things, you have all the boiler and everything, and the cab is at the back. Southern Pacific flipped them around, and basically they always ran backwards, so that the crew was in the front of the engine, because they went through all those snow sheds up in the Sierras, and these were designed to go in the snow sheds. Those engines used a lot of water. I think, what is it? There was an 8-mile stretch going over the Sierras for Southern Pacific. I think they used something like 22,000 gallons of water in one 8-mile stretch because of the steam they had to produce. This is why back in the day when they're building the railroad, there's all these little towns. If you go across the map, all these towns are a certain distance apart. Even in the Central Valley, towns were a certain distance apart. Well, this is where the train would go a certain distance, and that's where they had to get water. What about fuel? They would have to get water, because they're using up the water as they go along. So they'd only go a certain distance until they could get that water on that. In fact, even if you've ever seen pictures of the old trains, probably from the history books, you see these engines from like the Civil War era. They kind of look like this. They look kind of like that. You'd see like a bunch of wood piled up in the back here. Well, if you look at it from the top, and it looks like, oh, they're all filled with wood. If you look at the tender from the top, the tender actually looks like that. The wood was here. The rest of it was a water tank.
Can't even tell what that is.
Yeah, it looks like a train engine, right?
Oh, it's a train? Oh, man.
If you want to be technical, a 440 American type engine. If you've ever seen like Back to the Future, the engine they used in that, the engine in all the Civil War movies, the engines you see in the picture of the Transcontinental Railroad. This was basically the engine that was used before and during the Civil War. This was basically like what is called the American type. They made hundreds and hundreds of these engines back in those days. Oh, Salik, this is yours. All right, so back to our steam plant. Now, they all work the same. Now, this is what's called a closed cycle engine. Our train engine is actually called an open cycle engine because it brings in the water and expels the water. The water isn't reused. Car engines are open cycle engines too because they bring in air and they expel air. In other words, they don't do it. But this is closed cycle because it always reuses the water. And basically, we have this boiler that puts energy into the water. So our high temperature steam comes here. So there's our QH on this side. We have our QC on this side. Goes to the turbine, and that turbine might be hooked to could be hooked to a propeller. It could be hooked to a generator to make power, things like that. And we go to the T cold side, our condenser. Condensers are usually at low pressure, like below atmospheric pressure. They pull a vacuum. And then it goes through. Now the thing is, we said waste heat. This is waste heat, right? Well, usually this feed water is run back through the condenser because that colder water comes through. It helps condense, and also it picks up heat, so it goes back. Same thing on board the gas turbine ship. We had gas turbine powered generators. In other words, we had little jet engines that ran our generators. We use the exhaust from those generators in what we called a waste heat boiler. So the exhaust would boil water into steam that we used for cooking, because the kitchen, all the kitchen stuff worked on steam. We use it to heat the ship and to make water in different purposes on board the ship. But so the waste heat might be used for other things. It's not necessarily wasted, but it is the part that comes out on that side. To give an idea, other types of things here. So this would be kind of like, this would be more of an 1800s industrial type system. This is also how that train engine works. Those pistons on the front of the train engine, they work like this on that. So we put energy into the boiler, and it goes into our valve. And so notice one side is closed, one side's open, then down here it's open. So the steam comes in the piston, it pushes the piston one way, expels steam and water out the other. That's what you saw pouring out the bottom, was the steam and water coming out of the pistons, until it gets to the end, and then all those little bars, the big bar basically is connected to the wheels. That's what makes the wheels go around. But there's other little bars that would be connected to these valves. And when they got to a certain point, they shift the valves. So now we're going the other direction. So they notice this side closes, opens, and now the steam pushes it back that direction. So we're getting, unlike a car where the piston is only pushed down on this, notice this piston is being pushed both ways. So they get thing out there, and it exhausts out the other side on that. Okay. Now that's hooked, that linkage is hooked to some sort of flywheel. In the case of a train, it's hooked to a wheel, and then the other wheels are hooked to that wheel. All right, so the steam engine only drives one of those three wheels. The other ones get driven off that wheel. But in this case, this is a factory, so they'll be hooked up to all these belts and pulleys and things, and they go off to a mill somewhere and run all these machines. And so they would all work together. So you have your steam plant, divides it all up. And this is how factories were formed for years. You'd have a steam plant at the factory and all this. But this is basically, I put this steam plant on a train. It runs a wheel. I put it on a ship. Originally, it ran a paddle wheel. Eventually, I put this sideways and this rotating around. If I put a propeller shaft, it ran a screw propeller. This is before, the turbine was something that came around right after World War II. Around the time World War II is when they started putting turbines on ships. The steam turbine came around about that point. All right, questions? Yes. Yeah, go ahead. All right, so before we finish up with entropy, let's get your concept builders out. We're going to talk a few things about the concept builders, and we'll come back and finish up. So put your notes off to the side a little bit, take a little break from those. Let's look at the concept builders. Now, these concept builders, there are questions that are related to that. Now, one thing, there is a diagram. And I told you, put in your notes, we put in notes a couple of things. It's on page 348. It's that phase change diagram. It kind of looks like, you had this diagram that kind of looked like that. It had the calories at the bottom and things like that. That's a very useful diagram. In fact, I don't think a lot of you use that because a lot of the answers came right off that diagram. Which is why I said when we actually did this lesson, I said, this will be very useful when you do your concept builders. The two we did for this unit. 23, 1, and 2. But it'd be very useful for your charts, putting those little graphs and things like that, putting the values, latent heats and specific heats. They're going to be very important to that. So, if you looked at that graph, or get it from your notes, how many calories? So to get 1 gram to go from ice to water, ice to liquid water, how many calories do I have to put in? 80. It takes 80 calories. 80 calories, that's the latent heat of fusion. How many calories are needed to change the temperature of 1 gram of water by 1 degree Celsius? 1. It takes 1 calorie. That's specific heat. 1 calorie per gram per degree C. So if I wanted to go from 0 ice to 0 water, then up to 23 degrees, well, to go from 0 ice to 0 liquid, I have to put in how much? I have to put in 80. To go from 0 to 23, I'd have to put in 23, or a total of 103 calories. This is kind of like part of your lab, with that freezing lab. That was part of that freezing lab. That was the part of bringing the water up. Bring the water up. Well, let's be less. Honey nut or regular Cheerios? Honey nut. By much? No, not much. They're pretty close. In fact, if you look at the carton, they're pretty close there, too. I mean, the amount of calories you get out of one, I think there's like 10 calories different, maybe only 10 calories difference between Honey Nut and regular Cheerios in the serving size. All right. Now, 50 grams. So now we have a 50 gram sample of ice at 0 degrees. Place in a glass beaker that contains 200 grams of water at 20 degrees heat. This is basically your lab. So first of all, how much heat is needed to melt the ice? How much heat is needed to do 50 grams of ice? Well, 50 grams we multiply by what? Well, if it takes 80 for 1, it's going to take 4,050 times 80. Remember, 80 calories per gram. Remember, that's that latent heat. So we get 4,000 calories. You know, 80 for 1, we multiply by 50 to get the 50. How much would the temperature of the water change if it gave up this much heat? Well, then we have to look, okay, I want delta T. Remember, I'm not really looking for delta T here because where is this 4,000 calories coming from? It's coming from the 200 grams of water. Just like in your lab, when you threw the ice in, the heat to melt it was coming from the water that you put in the cup. So we could say 4,000 equals, because this is going to be Q equals MC delta T, equals that 200 times 1 calorie per gram degree C, our specific heat, times delta T. Remember, they want the change in temperature. They don't want how much it was, change in temperature. So we look at this, 4,000 divided by 200 is what? Which means, what's the final temperature? So remember, this mixture started at 20. It had a change of temperature of 20. Well, if I started at 20 and I lost 20 degrees, what's my temperature of the 200 grams at the end? 0. When I take 0 degree ice and I melt it, it ends up as 0 degree C liquid water. I like to use the term liquid because ice is water too. Ice is water, steam is water. I know they use water. When they say water, they mean liquid, but I kind of like to say liquid. Which means if they're both at 0, the final temperature is going to be 0 degrees. One went up, basically one melted, the other came down. In your lab, remember, you melted and then the temperature went up on that. All right, so how many calories are needed to change? And again, we're doing the same thing, but now we're at the latent heat of vaporization, which is 540 calories, 540. Same idea. So they're trying to get this same idea at the other end. Questions so far? This chart came from that graph. You guys know that all the answers were on this graph. Because this would have been that first part, right? This is this part right here. 80. We go to 1 calorie. Well, that was 100. It was on the graph, right? 100. 540. Whole thing would be 720. Came right off the graph. Good idea to have that on a note card. On your note card. Questions? Now we're kind of doing some things with the steam. They actually do this twice. We're only going to do the first part. They do it twice in here. So 1 gram of steam condenses and the water cools 22 degrees. So first of all, to go from 100 steam to 100 liquid, to go from 100 steam to 100 liquid, how much do you give up? We're going to give up 540 calories, right? 540 calories. All right, now to go from 100 to 22. Now, first of all, you might say immediately, oh, 22.